Hello, friends, and welcome once again to the third lecture. I'm Eli, and today we will be covering a bunch, probably more than we have in lecture 1 and 2. We will be covering just the same kinematics, momentum, and energy, but also we will be covering new topics such as torque, and a lot of rotation stuff. So we're gonna take our kinematic equations and we're gonna turn them into into rotational equations. So we're gonna do a lot of fun stuff. So without further ado, let's get into kinematics and then let's turn it into rotational kinematics. So we're going to want to start with kinematics, and we will want to derive all of our 4 equations right here. So of course we are starting with the assumption that acceleration is constant. Okay, and this is very important for this unit. We're assuming that acceleration is constant. Now, what is acceleration? Let's start from the beginning. Let's assume that we have, let me grab an object. I have a pen right here. I have this pen. And let's say that the reference point is the edge of the camera, all right, or of your frame. Hopefully you are seeing this like I am. Let's say that this pen moves all the way to the other end. It's been displaced, whatever distance this is, right? So we call that displacement because it's the distance that it moves, usually in units. Usually the unit is in meters. Then we have velocity. So what is velocity? Well, as it moves, you can see it takes it a certain amount of time. Say it took it 5 seconds, then we say that it moved this distance in 5 seconds. So the rate of change of displacement, that is the rate in which this pen is displaced, that's our velocity, right? You could think of it in terms of speed. Only the displacement also has it's what's called, it's a vector. So it has both a magnitude, like speed, and a direction, right? It's going from this end to that end. I'm not sure if that's going to be left or right for you, but it is in that direction that you see it. And then we have acceleration. So just as velocity is the change in displacement over time, acceleration is the change in velocity over time. Now, what does that mean? Let's see. Say this pen starts here, right? And it starts at, 0 velocity. I give it a push, and it starts moving, and it moves and it moves and it moves faster and faster and faster, right? So you can see that there is a change in velocity over time. That is acceleration. Acceleration is is the rate of change of the rate of change of displacement, or the rate of change of velocity. So that is what we are now gonna show we're gonna write using notation. So we have here acceleration is equal to the change in velocity over the change in time. And we can start now deriving our equations. So what is change in velocity? This is pretty simple. We begin with velocity 0. We end with a certain instantaneous velocity over here. Now, we can use some mathematical intuition, some calculus, and say when it reaches the end, we have a certain velocity f, an instantaneous velocity. Think of it as a limit. So then the difference in velocity will just be the final velocity minus the initial velocity. Simple as that. So we rewrite this as acceleration is equal to the velocity to v final minus v initial over difference in t. Now we're going to choose to solve for v final, and we have our first kinematic equation derived. V final is equal to v initial plus acceleration times time. Nice. Moving on to our second kinematic equation. There's many ways to do it, but I decided that a graphical way would be, more visual. It may be more interesting. So I drew here a graph that relates velocity to time. And we have a curve here. So if you can see this curve, this is a function of velocity over time. And notice that this is a linear curve, right? You can ignore this line here. I'll tell you what that's about in a second. But we have this linear curve that begins with v naught and ends with v over time t. Why is it linear? Well, first, we should remember a few things. Acceleration is constant, right? And now is where we kind of need to go back to calculus. How does acceleration relate to velocity, relates to displacement? Well, they relate to one another by derivatives and integrals. So if we think about it, we don't even need to think about it. Let's look at it. If acceleration is equal to the difference in v over the difference in t, let's take the integral of each side. So we integrate a, so the integral of a is equal to the integral of v over t. This is the integral with respect to t. So the t will drop out, and we just end up with v. So then the integral of a with respect to t, of course, is equal to v. What does that mean? That means that the integral of acceleration is velocity. Now we can repeat that same process because then we know that velocity is the difference in x, right? The difference in displacement over the difference in time. And if we take the integral of velocity, we will find that it's just equal to displacement, to difference in x. So what does this mean for our graph here? Well, it means that, or before even the graph, what it means is that acceleration is the derivative of velocity, is the derivative of displacement, or displacement is the integral of velocity, is the integral of acceleration. So if we have a function of v here, the area under the curve we know is an integral, right? So then the integral of the velocity function will give us our displacement function. So then all we need to do if we want to find out displacement using this graph is to find out the area under the curve of this velocity function. All right, let's do it. And this is where this line comes in. I just drew a line here to help us because now we can turn this shape into a rectangle and a triangle, which we know how to calculate the area of. So triangle, we just do base times height, right? Our base is t, our height is v naught, so the area here is v naught times t. So we're going to write this down. The displacement is equal to v naught times t plus the area of this triangle, which we know is 1/2 base times height. So 1/2, the base is t, the height is v minus v naught, so it's 1/2 t times v minus v naught. We're going to write that down here. Redistribute the pluses, we have displacement is equal to v naught times t plus 1/2 t times velocity minus 1/2 t times v naught. Now, we can take out the 2, we can take out a common denominator of t, and we get our second kinematic equation, which is displacement, difference in x, is equal to v plus v naught over t, all of that, or I'm sorry, displacement is equal to v plus v naught over 2, all of that times t. That is our second kinematic equation derived from a graph. So we can move on now to our third kinematic equation, which we will, it's very similar to the second one. We're just going to remember a little property. So when we have over here that displacement is equal to, and I rewrote this here, v naught times t plus 1/2 t times v minus v naught. What does v minus v naught mean? Could we rewrite this in a different way? Well, if you think about it, that's just acceleration times time, right? Because v minus v naught is, well, that's difference in v. Now, acceleration is the second, is it the second derivative? No, this acceleration is the derivative, right, of t with respect to t. So if we multiply by t, we're just going to get v minus v naught, which means that we can just rewrite this as v naught t plus 1/2 t times at. So we can multiply those t's and we get our third kinematic equation, which is that displacement is equal to v naught times t plus 1/2 a times t squared. That's our third kinematic equation. And now for our final kinematic equation, we're actually going to be using the equations that we've already derived, specifically equation 1 and equation 2. So if I rewrite equation 2 up here, we see that we have v plus v naught over 2, all that times t. And we're wondering if there's another way we can write t so that we can eliminate time from our equation and perhaps introduce, well, acceleration. That would be nice. So if we look at 1, we can actually solve for t, or yes, we can just solve for t, right? So we reorder this. We bring the v initial back here, so we have v final minus v initial. We divide it by acceleration. That is equal to t. there we go. So T is equal to V final minus V initial over A. Now we multiply out these both sides, and we get that V final squared minus V initial squared over 2A is equal to displacement, right? And we can rearrange this a bit to solve for V final. So we multiply everything by 2A, we bring the V initial squared to the other side, and just like that, we have our fourth and final kinematic equation. V final squared is equal to V initial squared plus 2 times acceleration times displacement. Now, these are very helpful because, of course, we have 4 equations that relate 4 unknowns, so we can always, depending on how much information we get, how many equations we need to use, we can basically figure out the rest using these equations. Very helpful, and I'm wondering if we can actually apply this to rotation, because thus far we've only been looking at linear displacement and acceleration and velocity. What happens if something is spinning? Say I have a pendulum that's going back and forth, or actually that'll come later, but what if I have something going in a circle, right? How do I relate this? Because the displacement, if you think about it, is 0, right? It keeps ending back in the same place. So is there something I could do now to turn these kinematic equations to work out with rotation? Yes, there is. And that's what we are going to do right ahead. But first, before we do all of that, we're going to take a quick look at energy. All right, we have laid out here energy. So we have the types of energy, and we're going to look at free body diagrams and springs at the very end. So we have a few types of energy that we should go through. First is potential energy. Now, potential energy could be, potential energy from gravity or due to a spring. And what does this mean? It means that, how about first we go over kinetic energy? So kinetic energy, as we intuitively would expect, it's like energy of stuff that are moving. So say I have this pen and I drop it down. When it's falling, it has the kinetic energy, right, of it going down. Now, potential energy is if, say, I hold it up over here. It currently has 0 kinetic energy. But if, say, my reference is the floor, and I remove my arm, this will fall down. So it has the potential to have kinetic energy, right, or to have energy, which is why potential energy has a lot to do with gravity, right? And with the height, if it's due to gravity. So we would write it's the mass times gravity times h. When I say gravity, I mean g. It's Earth's gravitational constant. This would be different under different, gravitational fields. And kinetic energy can be written as kinetic energy is equal to 1/2 mass times velocity squared. And we have internal energy, which is, say, for stuff like friction. Now, friction is a word we've heard, but what does it mean? Well, imagine we have a ball, or this pen, rolling down an inclined plane, right? If this is frictionless, it's just going to, roll right down. And yeah, it'll just roll right down, and there'll be potential energy because, right, it's up, and there'll be kinetic energy because it's rolling down. But if there's friction involved, then the friction is actually going to place a force on this, on the pen. Now, this is more easily imagined with, say, a box, because there are 2 types of frictions. There's the static friction and kinetic friction. What does it mean? Well, imagine you're trying to push a box, a heavy box. So you push it until you manage to make it move. So why would I move in the beginning? Well, that's because there's a force in the opposite direction that you're pushing on it because of Newton's second law, right, if we remember, which makes it so that you're not able to move it until you push with enough force that you overcome that friction, the static friction. But then when you manage to push it, it's not just going to, slide without you putting in any work, exerting any force on the object, right? You need to keep pushing it, but it's easier than it was before. That's because now you're overcoming not static friction, but kinetic friction. So kinetic friction is less than static friction, and we can model friction as, energy internal is equal to the force of friction right? Static or kinetic, times the distance that this object has traveled or the system has traveled. Now, over here I have a person pushing a box of mass m, and you can see that the force applied is going to the right and friction is going to the left. Now notice that I have two more arrows, and that's the force going downwards, mass times gravity. What does that mean? Well, that's the weight of the object, right? It's in the downwards direction. And the natural force is perpendicular to the surface. The natural force, that's just what it is, right? It's like if I push this wall, it's going to push me back with an equal in magnitude but opposite in direction force. Same with the box. The box is pushing down the ground, so the ground is pushing up on the box, and that's the natural force. So what is the force of friction? Well, force of friction is equal to mu, which is the frictional constant, times the natural force. And yeah, there we go, right? That's friction. That's friction, that's internal energy. Now, there's this idea of conservation of energy, which is very important, which is that energy can't be destroyed and can't be created. It can be converted to different forms of energy, though, right? So you can't just create energy and you can't destroy energy, but you can convert kinetic energy into heat energy, into sound. You can convert potential into kinetic. You can convert kinetic into potential, but you can never destroy or create energy as long as the system is isolated, which means that the energy initially will be equal to the energy in the end of whatever happened. That's a very helpful mathematical tool. We can tell ourselves that if the energy internal is equal to 0, that is, there's no friction because that's an external force, and there's no air resistance or something like that, then the difference then energy initial will be equal to energy final. So then we can write this differently as the difference in potential energy plus the difference in kinetic energy is equal to 0. Or, of course, the difference in potential energy is the negative of the difference in kinetic energy. That is, one is converted into the other. So now, what does springs have to do with this? Well, springs have a K constant, first of all, just like, friction. And we can compress them. And what we're doing is we're creating potential energy because the spring now can decompress and push the object, cause it to have kinetic energy, say, right? And this is also modeled by 1/2 K times x squared. And x, of course, is just the displacement of the spring from its natural state. And now we're ready to see how we can take our kinematic equations and play with them a little bit to model, well, rotation, as we were saying before. So let's get into it. All right, here we go. So we're going to do some rotation stuff. All right, how about we start by drawing a little circle here, right? And we have a line. Imagine we are swirling this thing over, right? And there's a few points of interest here. Now, when we twirl this is going all the way here. This is going all the way here. This is going all the way here. Now, notice how the line that is further, or the point that's furthest along on the line, travels the most distance, right? And the one that's closest travels the least distance. But they're all traveling the same angle, right? Now, this is why we want to relate linear properties with angular properties. And how do we do this? Well, let's go like this. Linear. And we want, well, let's do angular. All right, so first off, we have displacement, right? Let's try to think of all of our different properties. All right, let's just start by naming everything that we can. So we have x, right? We have velocity, x is displacement, velocity, acceleration, force. What else? About mass and momentum. Oh, let me fix that. So these all have their equivalents in angular form. So we've got theta for displacement, because of course it's an angle. We've got omega for velocity. We've got, well, lowercase omega for acceleration. For force, we have torque. For mass, we've got inertia. And for linear momentum, we've got angular momentum, which is an L. And the question is, how do we relate the two? Well, it all kind of has to do with the radius, right, of the center of rotation here. So we can say that x, displacement, is equal to r times theta, right? Oh, let me fix that. In the same way, velocity will be equal to r times w, and acceleration will be equal to r times omega. So then we can relate all of this because we can say that r, the radius, is equal to x over theta, which is equal to velocity, w, which is equal to omega over, to acceleration over omega. And then there's also our centripetal acceleration, which you can write a subscript c, which is just equal to v squared over r, but we can also rewrite this as r times w squared. So then that's great. We now have a way of relating angular units to linear units. So let's take this a step further and relate equations to one another. So let's start with our very simple kinematic equations. We have, on the linear side, we're going to have, let's start with our first one. Let's just do v is equal, v final is equal to v initial plus, what was it? Plus, let's do acceleration times time. The most simple one. We've also got our Newton's second law, right? So force is equal to mass times acceleration. We have momentum, so we could say momentum P is equal to mass times velocity. And finally, there should be one more. Let's do energy. How about we just take, for example, kinetic energy, which will be equal to 1/2 mv squared. Right, so now we want to turn all of these into, into angular equations. So v should turn into w. So we've got w final is equal to w initial, and w, remember, is just our angular velocity plus acceleration times time. So acceleration should turn into lowercase omega. Time, well, time is neither of these, right? It's not a linear unit, so we can just leave it in terms of time. All right, moving on to our Newton's second law. Force is equal mass times acceleration. Well, force in angular terms is just torque, right? So torque should be equal to angular mass, inertia, right? And this might be a bit hard to wrap our heads around, but it is that angular mass does exist, and it's inertia, times angular acceleration, which is just omega. Moving on to momentum, and yes, there is also angular momentum, right? Call it notified by L, is equal to mass times velocity, so it should be equal to inertia times angular velocity. And finally, energy. We could, well, how about this? We define Ke over here to be translational energy. And this Ke should be rotational energy, and we can set it to equal to 1/2 mass times velocity, so we want inertia times angular velocity squared. And there we go. We now have all of our linear equations converted to angular equations. And again, we can use these properties right here to relate the two and to move between them. So now we're probably left wondering, what are these? I think it's pretty intuitive what theta, W, and alpha are. But what about torque, inertia, and angular momentum? So torque is just, actually we can get into torque a little bit later, but inertia is the resistance that a body has to be moved, mostly to be rotated. So imagine we have a disc and I apply force on it, usually that force is torque. Then the amount of resistance it offers, that is its angular mass. That's probably one of the harder concepts to wrap our heads around in mechanics, but bodies do have angular masses as well. And now we can figure out what inertia is, because inertia should just be the sum. What should be the sum? It should be probably the sum of mass times its position r. But we would have to square it. So that's our inertia. Now what is torque? To understand torque, how about we draw a little pulley. And this pulley, we can say, is hung from a ceiling. And we apply a torque onto it. So this is our force applied. We're applying a torque onto it. Now, the amount that it would move is, of course, dependent on its inertia. And the disk has an inertia of 1/2 its mass times its radius squared. That is our inertia. And torque. So torque should always be R cross F perpendicular. What does this mean? We have a force applied, we have an R. Look at this, we have 90 degrees. So torque should be equal to the magnitude of our radius times the force applied in a perpendicular way. Now often, or not often, but sometimes that means that we need to play around with R and F. We need to break them into components, but that's probably beyond the scope of this lecture. We won't need to get too much into it. But this is the essence of torque. It should be radius times force perpendicular. Now, just like when we have, say, a body here, M, with different forces acting upon it, like say we have F1, we've got F2, over here maybe we're going to have force of friction. We can model this by using Newton's second law. So the sum of forces we're going to want in the x direction should be equal to, if we define this to be positive x, F1 plus F2 minus F of friction. We're going to call it static friction. And this should be equal to mass times acceleration, right? Well, we can do the same when it comes to, say, a pulley. If we've got a body here, this is its radius, we have a force applied here plus, say, a force applied here, then we can use, again, Newton's second law, only converted to angular, to angular units. And we should, first of all, think of the direction. So, right-hand rule, right? R cross F. So it's going in the positive direction, this one. R cross F, also positive direction. So we can just say that this is equal to, oh, I'm sorry, not force, over here. This should be torque is equal to F1 plus F2. And this should be equal to, instead of mass times acceleration, because remember we are in angular units right here, it should be equal to inertia times omega. And one last thing that we should mention. Imagine if we have, say, a ball rolling down an incline. What can we say about this ball's energy? Well, we learned before that we could model its energy as, its kinetic energy, 1/2 mv squared, right? But then that's just the translational energy. Now we another concept should be that kinetic energy total is equal to kinetic energy translational, which means in linear terms, plus kinetic energy rotational, which of course is in angular terms. So then Ke total should be equal to 1/2 mv squared plus 1/2 inertia w squared. And with that, I think we are done with the concepts, and it's time to move on. All right. Well, we've done the theory, right? We've done the theory that we wanted to cover, that we need this time. And I think, Mr. Paviko said this once, and I thought it was very, it's insightful, and I keep it with me that, and I might have already said this in a previous lecture, but you can learn a lot of. Okay, so it's time to begin on the problem that Mr. Paviko supplied. So let's read this out. A disk of mass m, which is 2 kilograms, and a radius r, which is 0.1 meters, is supported by a rope of negligible mass, as shown above. The rope is attached to the ceiling at one end and passes under the disk. The other end of the rope is pulled upward with a force Fa. The rotational inertia of the disk around its center is mr squared over 2, as we've shown before. So they want us at A to calculate the magnitude of the force Fa necessary to hold the disk at rest. Okay, so let's begin by drawing our situation. So we have ceiling here. We have this disk, and it's being held up by Fa. Is that correct? Yes, and they tell us that this is M and R, so mass is equal to, they say, 2.0 kilograms, and R is equal to 0.1 meters. Okay, so, and they tell us that the inertia, of this disk is equal to 1/2 mr squared. Okay, perfect. So again, they want us to calculate the magnitude of force Fa necessary to hold the disk at rest. So let's think this through. I'm thinking what we should do is Newton's second law, but in angular terms. So let's just set this up. We're going to want to do sum of torque is equal to, it's equal to F applied, right? But what do we do with the rope? Well, to better visualize this, let's draw a free body diagram. So we've got our disk here, we've got a force applied, and we've got tension, these should be roughly equal. And down from here we have our mass times gravity. So then the sum of torques, we remember it's R times F perpendicular. So it should be FA times R, right? Minus T times R. And Newton's second law, we remember this is equal to MA, which is inertia times alpha. And let's think, what can we do now that we know that? Well, maybe we should solve for alpha, since they ask us to calculate the magnitude of the force necessary to hold the disc. And then maybe we should do the same sum of forces with y. Yeah, let's do that. So let's leave some room. The sum of forces in the y direction should be equal to T plus force applied minus mg, and that should be equal to ma. So now there are two realizations that are going to help us solve this problem. And that's that in order for the, if the disk is not moving, then our acceleration is 0, which means that ma is going to be 0. And we know that tension should be equal to force applied, which means that we can rearrange this to say 2 times Fa should be equal to mg, or Fa is equal to mg over 2. Now we can plug in some numbers. So mass is 2. 2 divided by 2, that's 1. So it's just equal to g. It's just equal to g, which is equal to 9.8. And we want, this is going to be in newtons. So that is our final answer for A. Perfect. So let's see what part B is asking us. They say, at time t is equal 0, the force Fa is increased to 12 newtons, causing the disk to accelerate upwards. The rope does not slip on the disk as the disk rotates. B. Calculate the linear acceleration of the disk. All right, so we are going to use what we thought we would use in part A, which is the sum of torque. Let's make this more clear. This is B. So then this should be equal to inertia times alpha. All right, let's just expand on this. Down here, we have sum of torque should be equal to F R minus T R. This should be equal to inertia. So we have inertia is equal to just 1/2 mr squared. And what is alpha? Well, do you remember alpha is the same as acceleration over r. Okay, so we can cancel out these r's, right? We can also cancel out these r's. And what we're left is that force Fa minus T is equal to 1/2 ma. Now, this is not really good yet because we have T, which we want to get rid of. So what we're going to do is, again, we're going to do sum of forces in the y direction is equal to, how do we want to define this? We want to end up with a positive T here. So we can say it's equal to Fa plus T minus mg, and all this is equal to ma, right? Mass times acceleration. And now we can call this equation 1, this equation 2. Here's what happens if we combine equations 1 and 2. We say, here's equation 1, plus 2. So this is going to give us 2fa. And the plus t and the minus here are going to cancel out, which is perfect. That's what we wanted, right? We wanted, because we don't know what it is. So plus 0t minus mg should be equal to 1/2 ma plus ma. That's just 3/2 ma. And now we can just plug in some numbers. And let's remind ourselves again exactly what we're looking for. So they're asking for the angular speed, or the linear acceleration, right? So we're solving for a. So that should be pretty easy. You can say 2 times 12n minus 2 times 9.8 is equal to 3 over 2 times 2 times acceleration, or acceleration is equal to, let me grab my calculator, so it should be 1/3 times 2 times 12 minus 2 times 9.8, and we get our answer, which is, it's 1.47 meters per second squared. Don't forget the units. There we go. That's part B answered. All right, let's see what C is asking us for. Let's grab, So for C, they are asking us to calculate the angular speed of the disk at time equals 3 seconds. So this should be simple enough to do with our new and improved angular kinematic equations. So if we remember, angular speed is equal to, final is equal to angular velocity, initial plus acceleration times time. And we are looking, what did they say again? For the angular speed, yes. So all we need to do here is plug in the numbers. Well, initially it's 0, right? So this should be equal to 0 plus acceleration, which we have discovered to be 1.47 meters per second squared, times time, which is, we know, 30 seconds, because that's what they've said. And now let's grab the calculator. This here. So we have 1.47 7 times 3 4.41. Okay, so is that correct? So we forgot one thing, which is that this acceleration is not linear acceleration, but angular acceleration, which means that we're going to multiply it. And okay, here, we remember that angular acceleration is equal to acceleration over r, which means that we need to divide this by r, which we know is 0.1 meters. And now our calculation will work out to be 10 times the amount that we just got before, which is 44 radians per second. And that is our final angular velocity. Beautiful. Okay, so for part D, they're asking us to calculate the increase in total mechanical energy of the disk from time equals 0 to time equals 3 seconds. So what we're going to want to do is say, for D, that the change in energy is equal to the change in potential energy due to gravity plus the change in kinetic energy. But remember, kinetic energy of rotational plus kinetic energy of translational. So we know this is mgh plus 1/2 mv squared plus 1/2 I w squared. Okay, h. So we can figure out h because h is just the displacement. So using our kinematics, actually, we can just say that this is equal to 1/2 at, right? And over here we have not much to simplify, but we can say this is m times, well, do we know v? We don't know v, but we do know w. So we should just, well, we know that v is equal to w times r. Yeah, so w times r squared plus 1/2, and we know the inertia, so it's 1/2 mr squared times w squared. So now we have all of the numbers right, because we know m, we know g, we know a, we know t, we know m, we know w, we know r, we know m, we know r, we know w. All right, so it's just about plugging this into the calculator. Let's do that right now. And this is actually very long, so I'm just gonna plug these all off camera, and our final answer is, so we have 159 is our final answer. So our difference in energy should be 159 joules. Awesome. All right, and last question. This is a conceptual one, so it's going to be very short. They ask us, they say E. The disk is replaced by a hoop of the same mass and radius. Indicate whether the linear acceleration of the hoop is greater than, less than, or the same as the linear acceleration of the disk. So let's think about this a second. Linear acceleration we know is dependent on inertia, which would be the only change that has occurred over here. Would the inertia be greater or smaller? That's the question that they're asking, really. Well, if it has the same mass and the same radius, but it's more on the outside, that means it's going to be harder. It's going to give us more resistance, right? It's going to give us more resistance, which means that the inertia is going to be greater. Now, if the inertia is going to be greater, the resistance is greater, then when we apply a force, the acceleration will be smaller, right? So then our answer here should be less than. And that is our final FRQ, concluding the final lecture. Thank you very much for listening.